All right, everybody, welcome back to the last video of AP Calculus AB, at least assuming that I run in a timely fashion here. This is the second half of section 8.12, 8.12, where we're finding the volume of solids using the washer method around non-x or y axis. All right, so here we go, part C. We've done the two easy parts to this problem already, where we were revolving around lines that were parallel to the x-axis. It's a little bit more challenging in this problem when we revolve around lines parallel to the y-axis, and you'll see why momentarily. First things first, my axis of rotation here is x equals -4, which is this line right here. Now this line is parallel to the y-axis. So when I set up my integral here, I want everything to be in terms of y. Limits of integration in terms of y, and my integrands in terms of y. Now what happens here when I do this is I'm going to actually end up with two different integrals representing the volume of this solid, because right here there's a change in which curve forms the outer boundary of the region. Okay, the inner boundary is the same all throughout. It's this curve right here, this piece right here. But the outer boundary, I've got, it's this curve here, and it is this curve below that horizontal line. So we're going to need two integrals to find the volume of this solid. Let's start with the first one, the bottom one. So we are going to be integrating from here, this y-coordinate right here, up to this y-coordinate. So let's put our limits of integration in, 0.14020697 and 2.8806225. And now I need my curves. Now everything needs to be in terms of y here, so I have the equations in terms of x. For instance, this equation right here is y equals e to the x, and this equation right here is y equals 4 minus x squared. So I'm going to have to solve these equations and get them in terms of x as a function of y. This one's pretty easy. I take the natural log of both sides. I get that x is equal to the natural logarithm of y. This one's a little bit more challenging for us in the context here. I get x squared equals 4 minus y. I take the square root of both sides. So x is equal to plus or minus the square root of 4 minus y. And that's something to pay attention to here. The positive branch, the right branch is the positive branch here, the branch to the right of the vertex. That's our splitting point, the vertex of this parabola. The right branch is x equals positive square root of 4 minus y. The left branch is x equals negative square root of 4 minus y. So we're going to need to use those in this setup here. All right, so first of all, the region below my blue horizontal line here, the outer boundary is the distance from this curve to the axis of rotation. That's natural logarithm of y minus, because this endpoint is on the curve natural log of y, minus the lower endpoint, which is -4. And so this radius is going to be natural logarithm of y plus 4. And then my inner boundary is from this green highlighted curve over to the axis of rotation. Again, bigger minus smaller. The green highlighted curve is on the left branch of the parabola. So that's negative square root of 4 minus y minus -4. Makes that plus 4. Okay, so there's my first integral, getting what's below the horizontal line. And then above the horizontal line starts at this y coordinate right here, 2.88 0.06225 and goes to the y-coordinate all the way at the top here, which is a y-coordinate of 4. And then setting up my curves, I've got this pink curve, which is on the right branch of the parabola. So it's represented by square root of 4 minus y. So the distance from there to the axis of rotation is going to be square root of 4 minus y minus negative 4. And then my inner radius is on this green highlighted curve from there to the axis of rotation, which is going to be that negative square root of 4 minus y minus negative 4. And so I've got all this set up, and now I can go ahead and calculate these integrals in order to find the volume of the solid. So let me scroll myself up here a little bit, and time to go punchy on the keys. Pi times the integral of the quantity natural log of y, quantity squared, natural log of y plus 4, quantity squared, minus quantity negative square root of 4 minus y, close the square root, plus 4, close the quantity, squared, with respect to y, from 0.14020697 to 2.88062225 plus pi times the integral of the quantity square root of 4 minus y plus 4 quantity squared minus quantity negative square root of 4 minus y plus 4 quantity squared, 4 quantity squared with respect to y from 2.88062225 up to 4. All right. And assuming I punched all of that in correctly, this should give us the volume of this region. 144.880 is going to be the volume of this solid. Okay, now, in the next one, I'm going around x equals 3. So I've got a vertical line over here at x equals 3. But the same concepts tie in for us. We've got a horizontal line here that divides this into two integrals. The only difference now is when I'm finding the radii, it's going from this line over to the curve. There's my outer radius and my inner radius for the top piece. Here's my outer radius and my inner radius for the bottom piece. And so we'll go ahead and set those up. We've already found and solved all the curves and figured that out for ourselves. So I'm just going to be swiping back and forth on the page here to get myself set up. Let's get the bottom piece below the blue horizontal line. We've got pi times the integral from 0.14020697 up to 2.88062225. And our outer radius is the distance from this line over to the left branch of the parabola. So the line is at 3. So we've got 3 minus the left branch of the parabola was negative square root of 4 minus y. So 3 minus negative square root of 4 minus y becomes 3 plus square root of 4 minus y, that whole quantity squared, minus the inner radius, which is going to be 3 minus the right-hand branch, which was positive square root of 4 minus y. And there's my setup for everything below the blue horizontal line. And I'm going to add to that pi times the integral from 2.88. Wait a second, what did I do there? Oh, I did the above. I did the curves above, so I'm going to change my limits of integration instead of changing my curves. I'm going to change my limits of integration on here. Oh my goodness. I just turned that into a mess. This was 3 plus square root of 4 minus y. And my limits of integration are for the top piece. So that's 2.8806225 to 4. That's the stuff above the horizontal line. And then below the horizontal line, I've got pi times the integral from 0.1402067 to 2.8806225. And the outer radius is from the axis of rotation over to the left branch of the parabola. So that's the same as the first part here. And then the inner radius is the distance from this axis to the, what is that, the natural log of y. All right, and there's our setup to find the volume in this case. And now it's just a matter of typing it in and getting my volume. So I'm going to have pi times the integral of the quantity 3 plus square root of 4 minus y, square that quantity, minus quantity 3 minus square root of 4 minus y, close the root, close the quantity, square the quantity with respect to y, from 2.8806225 up to 4, plus pi times the integral of the quantity 3 plus square root of 4 minus y, close quantity, square that, minus quantity 3 minus natural log of y, square that quantity with respect to y, from 0.1402069 to 2.8806225. And assuming I typed everything in correctly, this is going to give me the volume of this solid. Take my calculator a few moments here to churn out those values. And we got 137.824 for the volume. And I'm going to just give myself a quick check and make sure I typed everything in correctly. Pi, integral, lower limit of integration, 3 plus square root of 4 minus y, minus 3 minus square root of 4. Okay, that one looks good. This integral looks good. So feeling pretty good about that. All right, that brings us to the end of this lesson on finding volumes of rotational solids using the washer method, where we're going around lines other than the x-axis and the y-axis. And that brings us to the end of the course for those of you who are in Calculus AB. Time to get ready to review and get ready for your AP exam. So we'll start that soon. All right, everybody, have a great rest of your day, and I'll talk to you the next time I'm talking to you. Bye-bye for now.